everyone, and welcome to this opening video lecture for the course of Calculus and Linear Algebra. My name is Dr. James Gaunt, and I'll be covering the linear algebra component of the course. Before I wanted to start on any sort of technical mathematics jargon, I thought I would give this opening video that's kind of a brief introduction, an overview of some of the things that we're going to talk about in this course. So you get a big picture of where we're starting and where we're going, and how these different areas of maths that we're going to be introducing will intersect with one another, as well as intersecting with the calculus component of the course that's been covered by Dr. Ria Simmons. So what I'm going to do is I'm going to give like a little pictorial sketch of how all these components are built on top of each other in this part of the course, and hopefully that will give you an idea of how they all overlap. So I'll just move over to the tablet, and let's just analyze the title for a moment. So you might already be familiar with some area of calculus, because these are things that you've seen in A-level, where you've discussed things like integration and differentiation. But the word that might be very new to you is the word linear algebra. And this is the part that I'm going to be looking at, which is really about a certain type of structure on some sets that we'll get into in a minute. But in my part of the course, I'm also going to address some kind of deeper questions about the structure of mathematics itself. And where we need to start in our story is we need to start with something that is otherwise known as logic. So the kind of bedrock of my part of the course is going to be logic. So logic, what is logic? It's the framework on which any sort of mathematical argument or proof is going to be built upon. So when I make some sort of mathematical statement, like if such and such is true, then such and such are true, I need to be able to know how to connect those two statements in some sensible way. And logic is the language in which we do that. So really logic is the core to pretty much any component of mathematics that you talk about, or any rigorous argument. So whenever I want to produce some mathematical proof, in whatever framework it might be, whether or not it be in calculus or the linear algebra component or some other exotic areas of mathematics, logic is the thing that allows me to construct those proofs in a sensible way. So once we've built this framework of logic, the next thing we want to do is we want to play around with some objects, right? What are the most basic objects that we can start talking about in which logic can be imposed upon? And the most basic objects that we can think about in mathematics are the things that have no structure on them, right? And that would be just a collection of things, collection of objects. And those collections of objects can be grouped together in any sort of way. So it's a collection of unordered objects. And that otherwise is known as, if you're aware of this, is just a kind of another way of saying that's a set. So the next component of the course that logic will move to is going to be set theory. And that's exactly as it says on the tin. Namely, it's just the theory and structure that we're going to build on sets. And we're not going to really delve into that too much, because the kind of higher level areas of set theory require kind of a much deeper level knowledge of maths and are normally further down the line in your mathematical careers. So for now, we will just introduce some basic ideas of sets, what a set is, and some of the things that you can do with sets, how to say two sets are equal or something like this. And it might seem like the next step is to build some structure on those sets. Like I said before, like with linear algebra, that was something where you build some structure on sets. Now, instead, we're going to take a little bit of a back step, and we're going to talk about how to construct certain types of mathematical proofs. So the next component of the course will be constructing mathematical proofs. So I'll just write this as maths proofs. So that is, given a mathematical statement of a particular type, how can I use my framework of logic down here and my knowledge of sets to be able to prove that that statement is indeed true? And in mathematics, we're going to end up with all sorts of different statements, but these statements can be grouped together in kind of a very particular way. And using the two previous pieces of the course that we've already introduced at that point, we can then figure out a way of how to prove certain types of mathematical statements. And this will be particularly useful for all areas of mathematics, and it will even tie very nicely into the calculus component of the course, because you will see certain types of mathematical statements that arise in calculus. They'll be very different to the ones that we see in linear algebra, but you can use the same proof techniques, the same logic, to be able to prove that particular statement. So it's kind of something that broadens all of mathematics. It encompasses all of mathematics, and it's really important that you understand how to be able to construct them. And then that brings us to the final component of the course. So we have our logic, on which we can use to build our maths proofs, and we also have our sets, which are most basic objects we have in mathematics, just collections of unordered objects. And we then want to say, well, now let's put some structure on those sets. Maybe it is addition or multiplication or something like that. And that leads us into the next and final topic, which is going to be the largest topic, which is linear algebra. And what do we mean by linear algebra? We simply mean that the word linear generally refers to the particular type of structure we're talking about. And in this case, it's going to be a way in which we can add two elements of a set down here, and we can multiply an element of a set and scale it by some arbitrary factor. And algebra is just a fancy word for saying that we're putting structure on sets. So the word linear, just to reiterate again, is a way in which we can add things and a way in which we can scale them. So you might have seen in linear algebra, we talk about things like vectors, which is a big component of the course. And a vector you might have understood as something that has a direction and a magnitude. And you can really think of it that way, right? A vector is something that you can add. You can add two vectors together, and you can also scale a vector by an arbitrary number. So in that sense, a vector is encompassed by the area of linear algebra, but we can talk about much more general things in maths that we can also add and scale by arbitrary numbers. And any of those things we call vectors. And that's what linear algebra discusses. It discusses the mathematics of those particular types of structures. So I think that's where I'm going to conclude this opening video. That's a brief overview, very quick overview of the things that we're going to be talking about throughout this academic semester and the following academic semester. So hopefully that's kind of enthused you about some of the things that we're going to be talking about. And in the next video, what I'm going to do is I'm going to introduce this kind of bedrock component, which is logic. And we're going to start off by talking about something called propositional logic, which is built upon, as you might expect, the most fundamental principle, which is propositions. So that's what we're going to talk about next time. And I hope to see you there. And thank you very much for watching this video. And I look forward to learning some interesting maths with you across this academic year. Thanks.